This video is on hypothesis testing. If you've taken a statistics class before, you probably know that there are different types of hypothesis tests. This video is just meant to introduce you to the overall topic of hypothesis testing. I won't get into the details of the different types of hypothesis tests until later videos. Basically, hypothesis testing is used to reach conclusions during research studies. It's the use of calculations to reach a conclusion at the end of a study. Since this video is meant to introduce you to hypothesis testing, I won't cover the calculations that are used during research studies. Instead, I will talk about how hypothesis testing can be used to reach conclusions during daily life situations. I'm hoping that this will make it easier for me to introduce the vocabulary and calculations that are used during hypothesis testing. And I'm hoping that it will also make it easier to understand the calculations and vocabulary once we start to talk about research studies later on. The purpose of a hypothesis test is to collect evidence to decide between two competing possibilities, called a null hypothesis and an alternative hypothesis. I'll start by giving you a basic or common sense definition of these two terms. The null hypothesis is the possibility of the absence of something. The alternative hypothesis is the opposite of the null hypothesis. It's the possibility of the presence or the existence of something. Now let's look at some different situations and try to find out what the null hypothesis and alternative hypothesis would be. Imagine that someone wants to know if they have a cold. In this situation, the null hypothesis would be that the person does not have a cold. The null hypothesis would be the possibility of the absence of the cold. Remember, the null hypothesis is the possibility of the absence of something. The alternative hypothesis is the opposite possibility. The alternative hypothesis is the possibility that the person does have a cold. So it's the possibility of the existence of the cold. It's the possibility that the cold does exist. So this is situation one. What's another situation? Maybe a person wants to know if there's a mouse living inside the walls of their home. In this situation, the null hypothesis would be the possibility that there is no mouse living in the walls of their home, and the alternative hypothesis would be the possibility that there is a mouse living inside the walls of their home. So the null hypothesis is the possibility of the absence of the mouse. It's the possibility of no mouse. The alternative hypothesis is the opposite possibility. It's the possibility that the mouse it's the possibility that there is a mouse inside the walls of the home. So it's the remember that the alternative hypothesis is the possibility of the presence or the existence of something. So in this situation, the alternative hypothesis is a possibility that the mouse is there. So the null hypothesis says no mouse. The alternative hypothesis says there is a mouse, because the null hypothesis is the possibility of the absence of something, and the alternative hypothesis is the possibility of the presence or the existence of something. Let's look at one more situation. What if a person wants to know if his or her computer has a virus? The null hypothesis would say that there's no virus, and the alternative hypothesis would say that there is a virus. Because the null hypothesis is the possibility of the absence of something, and the alternative hypothesis is the possibility that either something is present or something exists.
In each of these situations, the person would like to know if the null hypothesis or the alternative hypothesis is true. What types of evidence could the person gather in each of these situations to decide whether the null or the alternative is true? In situation 1, in which the person wants to know if he or she has a cold, the person could count the number of times that he or she sneezes during the day. If the person sneezes only a small number of times during the day, like 1 or 2 times, then the person won't be convinced that he or she has a cold, because a person could easily sneeze 1 or 2 times just by chance. So if the person only sneezes a small number of times, the person will assume that the null hypothesis is true and that the person doesn't have a cold. But if the person sneezes a large number of times, like 10 times, then the person will be convinced that he or she has a cold, because a person wouldn't be likely to sneeze 10 times just by chance. So if the person sneezes if the person sneezes a large number of times, then the person will be convinced that the null hypothesis is wrong and that the alternative hypothesis is true. In other words, if the person sneezes a large number of times, the person will be convinced that he or she does have a cold. What about in situation 2? In this situation, the person wants to know if there's a mouse living inside the walls of the home that they live in. In this situation, maybe the person could count the number of noises that they hear during the day. Maybe the person could count the number of noises they hear from inside the walls of the house. And this works the same way as in situation 1. If the person only hears a small number of noises, like 1 or 2 noises during the day, then the person won't be convinced that there's a mouse living inside the walls of the home, because those 1 or 2 noises could easily happen just by chance. They could just be random noises. So if the person only hears a small number of noises, the person will assume that the null hypothesis is true, and that there's no mouse living inside the walls of the home. But if the person hears a large number of noises, like 10 noises during the day, then the person will probably be convinced that there is a mouse living inside the walls of the home, because it isn't likely that the person would hear 10 noises during the day just by chance. So if the person hears a large number of noises, the person will be convinced that the null hypothesis is wrong and that the alternative hypothesis is true. In other words, the person will be convinced that there is a mouse living inside the walls of the home. What about in situation 3, in which the person wants to know if the computer has a virus? In this situation, the person could count the number of times that his or her computer freezes during the day. And just like before, just like in these other examples, if the computer only freezes a small number of times, then that's not really good enough evidence to conclude that the computer has a virus, because the computer could freeze 1 or 2 times easily, even without a virus, but it's unlikely that the computer would freeze a large number of times just by chance. So if the computer freezes 1 or 2 times, then the person will assume that the null hypothesis is true and that the computer doesn't have a virus. But if the computer freezes a large number of times, then the person will be convinced that the computer has a virus. In other words, if the computer freezes a small number of times, the person will assume that the null hypothesis is true. But if the computer freezes a large number of times, the person will be convinced that the null hypothesis is wrong and that the alternative is true.
In each of these situations, there's 2 possible decisions that can be made. If enough evidence has been collected, the person will decide that the null hypothesis appears to be wrong and that the alternative hypothesis appears to be true. That decision is called rejecting the null hypothesis. If not enough evidence has been collected, the person will continue to assume that the null hypothesis is true. That decision also has a name. It's called failing to reject the null hypothesis. What that pretty much means is that the null hypothesis has not been rejected. The null hypothesis continues to get the benefit of the doubt. So, if I sneeze 1 time during the day and I'm not convinced that I have a cold, and I just continue to assume that I don't have a cold, and I continue to assume that the null hypothesis is true, that's called failing to reject the null hypothesis. It's pretty much just a non-rejection of the null hypothesis. If I sneeze 10 times and I decide that the null hypothesis is wrong and that I do have a cold, that's rejecting the null hypothesis, because I've rejected the possibility that I don't have a cold, and I've concluded that I appear to have a cold. So you either reject the null hypothesis and conclude that the alternative appears to be true, or you don't reject the null hypothesis and you just continue to assume that the null is true. If I only hear one noise during the day, and I assume it's just a random noise, and I'm not convinced that there's a mouse living inside the walls of my house, then I've failed to reject the null hypothesis. In other words, I haven't rejected the null hypothesis. I'm continuing to assume that the null is true. That's what failing to reject the null hypothesis means. If I hear 10 noises during the day, and I'm convinced that there is a mouse, and I conclude that there is a mouse living inside the walls of my home, then I've rejected the null hypothesis because I've rejected this possibility that there is no mouse, and I've decided that I think that there is a mouse. Over here in situation 3, if my computer only freezes 1 or 2 times, and then I assume it's just something that's happening randomly, and that my computer doesn't have a virus, then I'm just sticking with the null hypothesis. I'm not rejecting it, and that decision is called failing to reject the null hypothesis. Failing to reject the null hypothesis means you give the null hypothesis the benefit of the doubt because you haven't collected enough evidence against it. If my computer freezes a large number of times, and I conclude that my computer does have a virus, then I've rejected the null hypothesis. I've rejected the possibility that my computer is fine, and I've decided that my computer does have a virus. I've decided that I think the alternative is true. So in each situation, you either fail to reject the null hypothesis or you reject the null hypothesis, depending on how much evidence you've collected, depending on how strong the evidence is. And let's try to visualize the evidence on a number line in each of these situations. So before I do this, I wanted to say that the overall logic of hypothesis testing is that if an outcome happens that would be unlikely to happen in the situation of the null hypothesis being true, then you reject the null hypothesis. If I sneeze a large number of times during the day, then I would reject the null hypothesis because that's something that would be unlikely to happen when the null hypothesis is true. In other words, it's something that would be unlikely to happen on a day when I don't have a cold. But if I only sneeze a small number of times, like 1 or 2 times during the day, then I wouldn't reject the null hypothesis because that's something that could easily happen when the null hypothesis is true. In other words, it's something that could easily happen just by chance. I'll write out the logic of hypothesis testing at the top of the screen. The overall logic of hypothesis testing is reject the null hypothesis if an outcome happens. It would be unlikely to happen if the null hypothesis was true. Or you could say, if an outcome happens that would be unlikely to happen in the situation of the null hypothesis being true. Otherwise, continue to assume that the null hypothesis is true. If I keep hearing noises from inside the walls of my house all day long, then I would reject the null hypothesis because that's something that would be unlikely to happen in the situation of the null hypothesis being true. In other words, it's something that would be unlikely to happen in the situation of there being no mouse inside the walls of my house. The reason why is because in the situation of the null hypothesis being true, and there being no mouse inside the walls of my house, any noise that I hear is happening by chance. It's just some random noise, and I'm not likely to hear a large number of noises just by chance. That's why if I do hear a large number of noises, I would reject the null hypothesis, and I would decide that there is a mouse living in the walls. But if I don't hear a large number of noises, then I wouldn't reject the null hypothesis. If I don't hear any noises, or if I only hear a small number of noises, then I'll continue to assume that the null hypothesis is true, and that there's no mouse. The reason why is because I could easily hear a few noises during the day just by chance. Now let's go back to this number line. This number line is showing number of sneezes. We have one outcome that's perfectly consistent with the null hypothesis, meaning it shows no evidence against the null hypothesis, and that outcome is 0 sneezes. So if I sneeze 0 times during the day, that gives me no reason to think that I have a cold. It perfectly lines up with the idea that I don't have a cold, meaning it's perfectly consistent with the null hypothesis. But outcomes further and further above 0 show more evidence against the null hypothesis, meaning outcomes further above 0 give me more and more reason to think that the null hypothesis is wrong and that I do have a cold. So as we go up the number line, we have more evidence against the null hypothesis. And at a certain point along this number line, I'm going to be convinced that I do have a cold. I'm going to be convinced that the null hypothesis is wrong. The reason why outcomes further above 0 show more evidence against the null hypothesis is because outcomes further above 0 are less likely to happen in the situation of the null being true, meaning they're less and less likely to happen on a day when I'm healthy and I don't have a cold. So outcomes further above 0 are showing more evidence against the null hypothesis because they're getting less and less likely to happen in the situation of the null being true. And I said at a certain point, I'm going to be convinced that I do have a cold. At a certain point, I'm going to reject the null hypothesis and conclude that the alternative appears to be true. And I'm going to need to set some cutoff point where I'll be convinced that I do have a cold. Maybe I decide that if I sneeze 4 or more times, I'll reject the null hypothesis and conclude that I do have a cold. But if I sneeze less than 4 times, I won't be convinced. If I sneeze less than 4 times, I'll just assume that the null is true and I'll assume that I don't have a cold. So I've set a cutoff point that's the minimum number that I need to reach in order to reject the null hypothesis. And this minimum cutoff point is called a critical value. So let's talk about two new terms here. The value that shows the amount of evidence that we have against the null hypothesis is called the test statistic. In this example, the test statistic is the number of sneezes. The critical value is the minimum value that the test statistic has to reach in order to reject the null hypothesis. So I said that the test statistic is the value that shows the amount of evidence that you have against the null hypothesis. So a test statistic of 0 means you have no evidence against the null hypothesis. If I sneeze 0 times, I have no evidence against this possibility of the null. In other words, I have no reason to think that I have a cold. But higher and higher values of the test statistic show more and more evidence against the null hypothesis. They give me more and more reason to think that I do have a cold. So when the test statistic equals 0, there's no evidence against the null hypothesis. But higher values of the test statistic show more and more evidence against the null hypothesis. And the critical value is the minimum amount of evidence, meaning it's the minimum value that the test statistic has to reach in order to reject the null hypothesis. If the test statistic falls short of the critical value, you don't reject the null hypothesis. You just assume that it's true. There's also a name for all of the values of the test statistic that start at the critical value and are higher above the critical value. This area of the number line that includes all numbers that are 4 and above is called the rejection region. The rejection region is just the collection of outcomes that lead to the rejection of the null hypothesis. So all values that are at the critical value or higher are in the rejection region, because all values at the critical value and above lead you to reject the null hypothesis. So this is the rejection region. Remember that the critical value is a part of the rejection region. It's the lowest part of the rejection region, because if your outcome is right at the critical value, you do reject the null hypothesis. If I sneeze 4 times and my outcome is right at the critical value, I do reject the null hypothesis. In this example, any outcome that is at 4 or higher would be in the rejection region and would lead me to reject the null hypothesis. So if I have 4 sneezes, I reject the null hypothesis. If I have 5 or 6 sneezes, I reject the null hypothesis. And if I had more than 6 sneezes, I would reject the null hypothesis. All of these outcomes that are at the critical value or higher and are in the rejection region are the outcomes that are so unlikely to happen when the null hypothesis is true that you reject the null hypothesis when one of those outcomes does happen. Let's now think about what the test statistic would be in situation 2, in which there's a person who's wondering if there's a mouse living inside the walls of their home. Remember that the test statistic is the number that you're using to decide whether the null hypothesis should be rejected. In the first situation, the test statistic was the number of sneezes, because we were using the number of sneezes to decide whether we should reject the null hypothesis of not having a cold. In this situation, we're using the number of noises from inside the walls of the house to decide whether the null hypothesis of no mouse should be rejected. So in this situation, the test statistic is the number of noises that we hear from inside of the walls of the home. In this situation, we're on a certain day, we're counting the number of noises that we hear from inside the walls of the home, and we're using that number to decide whether the null hypothesis should be rejected. So the number of noises that we hear on that day is the test statistic. And this test statistic works the same way as this test statistic did over here, because 0 would be the lowest possible value of the test statistic, because 0 noises is the lowest number of noises we could hear, because we can't hear a negative number of noises. So we might hear 0 noises, we might hear 1 noise, or we might hear 2 noises. Let's make a number line of some of the possible number of noises that we might hear from the walls of the house. And once again, 0 is the outcome that's perfectly consistent with the null hypothesis, because if we hear 0 noises, we have no reason to think that the null hypothesis is wrong. We have no reason to think that there's a mouse living inside the walls of the house. So 0 is perfectly consistent with the null hypothesis of no mouse. And values of the test statistic that are further above 0 show more and more evidence against the null hypothesis, just like how they did in the first situation over here. So if we hear 4 noises, that's more evidence for a mouse than 3 noises, and 3 noises is more evidence than 2 noises, and 2 noises is more evidence than 1 noise. So the further we go up on this number line, the more and more evidence we have against the null hypothesis. And once again, the reason why outcomes further above 0 show more evidence against the null hypothesis is because outcomes further above 0 are less and less likely to be found in the situation of the null hypothesis being true. Because in the situation in which the null hypothesis is true and there's no mouse living inside the walls of the home, any noise that we hear from inside the walls is happening by chance. It's a random noise. And we might be likely to hear 1 or 2 random noises during the day just by chance, but the further you go up on this number line, the less and less likely you are to get one of these outcomes just by chance. At a certain point on the number line, we're going to be convinced that that the noises we're hearing aren't just happening by chance, and that there actually is a mouse inside the walls of the home. And that minimum point will be our critical value. Once again, the critical value is the minimum number that the test statistic has to reach in order for you to be convinced that the null hypothesis is wrong. It's the minimum value of the test statistic that has to be reached in order to reject the null hypothesis. And let's say that in this case, if I hear 6 noises from inside the walls of the home during the day, that's the point where I'll be convinced that there is a mouse inside the walls of the home. That's the point where I'll reject the null hypothesis of no mouse and decide that I think that there is a mouse. So that means that I'm setting 6 as my critical value. And so if I hear fewer than 6 noises, I don't reject the null hypothesis. I just continue to think that the null is true and that there's no mouse. But if I hear 6 or more noises, then I reject this possibility of no mouse. I reject the null hypothesis, and I conclude that I think the alternative is true and that there is a mouse. And in situation 3, it works the same way again, because once again, we'll have a number line. Our test statistic this time will be the number of times that the computer freezes during the day. Because in this situation, we're counting the number of times that the computer freezes during the day to decide whether or not we think that there's a virus inside the computer. And just like before, an outcome of 0 would show no evidence against the null hypothesis. Because if the computer freezes 0 times, and if the test statistic is at 0, there's no reason to think that the computer has the virus. If there's 0 freezes, you would just assume that the computer does not have a virus. And more and more, or a higher and higher number of freezes would give you more and more reason to think that the null hypothesis is wrong and that the alternative is true. And at a certain point, you'll be convinced that that the null hypothesis is wrong and that the computer does have a virus. Because if the computer freezes enough times, you'll think that the computer isn't likely to freeze that many times just by chance. So there should be a reason why the computer is freezing besides just chance. And you might be wondering if there's a rule for deciding what number the critical value should be. In statistics, the rule that's usually used is that the critical value is set at the number that only has a 5% or 0.05 probability of being reached when the null hypothesis is true. Now I'm going to do another example to help explain this 0.05 rule for setting the critical value. In this situation, a person is climbing a mountain, and we're wondering if this person trained for the climb. So, in this situation, the null hypothesis would be the possibility that the person didn't train for the climb. It would be the possibility of no training, because the null hypothesis is the possibility of the absence of something. It's a possibility that something is missing. And the alternative hypothesis would be the opposite possibility. It would be the possibility that the person did train for the climb. So, how can we make this decision? Well, we could observe this person climbing the mountain and look to see how far up the mountain the person is able to make it before the person can't make it any higher. The further that the person is able to make it up the mountain, the more evidence we'll have for the alternative hypothesis, because a person who didn't train isn't likely to make it up to a high point on the mountain. A person who didn't train might easily make it to a low place on the mountain, but higher and higher places up the mountain are less and less likely to be reached by someone with no training. So let's mark off some altitudes on the mountain right here. Let's say that the mountain is 5,000 feet tall. So this is 1,000 feet, this is 2,000 feet, this is 3,000, 4,000, and 5,000. As we go up higher and higher, these outcomes are getting less and less likely to be reached by someone with no training. In other words, they're less and less likely to be reached when the null hypothesis is true.
and the climber has no training. So if a person makes it up the mountain to a certain point, we'll be convinced that the person did train. In other words, there's going to be some point on this mountain where if the person makes it up that high, we'll be convinced that the person did train for the climb. And that'll be our critical value. That'll be the point where we'll reject the null hypothesis and conclude that the person did train for the climb. But how do we decide what the critical value should be? In order to decide what the critical value should be, you have to know what point on the mountain only has a 0.05 or 5% probability of being reached by a person with no training. In other words, we have to know what point on the mountain only has a 0.05 probability of being reached when the null hypothesis is true. Let's say we know that out of all people who try to climb the mountain without any training, 60% make it into this area below 1,000 feet before they can't make it up any higher. 30% make it into this area between 1,000 and 2,000 feet before they have to stop and can't go up any higher. Let's also say that we know that 6% make it into this area between 2,000 and 3,000 feet before they can't go up any higher. Let's say that 4% make it into this area between 3,000 and 4,000 feet. And let's say that only 1% of all people who try to climb the mountain with no training make it into this area between 4,000 feet and 5,000 feet at the top of the mountain. Since 4% and 1% add up to 5%, we can see that out of all people who try to climb the mountain without any training, only 5% of them make it into this area of the mountain. Only 5% make it into this green area between 3,000 feet and the top of the mountain at 5,000 feet. So this area right here is only reached 5% of the time when the null hypothesis is true and the climber has no training. So since only 5% of climbers with no training make it into this area right here, this climber that we're watching only has a 0.05 or 5% probability of making it into this area. This person right here has a 0.05 or 5% probability of being one of the lucky 5% that are able to make it this far up the mountain with no training. What that means is that 3,000 feet is the point on the mountain that has a 0.05 probability of being reached when the null hypothesis is true and the climber has no training. So that means that 3,000 feet is our critical value. If this person makes it to 3,000 feet or higher, meaning if the person lands somewhere in this green area, we'll reject the null hypothesis and conclude that the person did train for the climb, because the idea is that if the person didn't train for the climb, then the person would be unlikely to make it up this high up the mountain. The person would have to be lucky to make it up that high up the mountain with no training. So 3,000 feet is our critical value. Everything between 3,000 and 5,000 feet in this green area is the rejection region. Because if this person lands somewhere in this area, we reject the null hypothesis and conclude that the person did train for the climb.
Remember I said that the critical value is the starting point of the rejection region. So 3,000 feet is our critical value. (3,000 feet) is the point where we'll be convinced that the person did train for the climb. And if the person doesn't make it up to 3,000 feet and lands somewhere in this black area down here, then we won't reject the null hypothesis. We'll just continue to assume that the person didn't train for the climb. We'll stick with the null hypothesis. So in other words, if the person lands somewhere in the black area below the critical value, we'll fail to reject the null hypothesis, meaning we'll continue to assume that the null is true. But if the person makes it to this point at 3,000 feet or higher, we'll reject the null hypothesis and conclude that we think the alternative is true and that the person did train. But if the person makes it into the rejection region, that doesn't prove that the person trained for the climb, because it could be that the person didn't train and the person was just lucky enough to make it that high up the mountain. So if the person makes it into the rejection region and we conclude that the person trained for the climb, there's a certain chance that we might be making a wrong conclusion. But the evidence, if the person makes it up this high up the mountain, the evidence is strong enough for us to at least conclude that we think that the person trained for the climb. Whenever an outcome lands in the rejection region, there's two possibilities. Either the null hypothesis is true and an unlikely outcome happened, or the alternative hypothesis is true. And in this case, what that means is that if the person makes it into the green area up here, the two possibilities are that the null hypothesis is true and the person didn't train, and the person was just lucky enough to make it that high up the mountain, or the alternative is true and the person did train for the climb. Even though either of those possibilities could be correct, it makes more sense to reject the null hypothesis and conclude that the person did train for the climb than to conclude that the person didn't train and was lucky enough to be one of the 5% of untrained climbers who make it that high up the mountain. We talked about what the rejection region and the critical value are in this example. Now let's think about what the test statistic is in this example. Remember that the test statistic is the value that shows how much evidence you have against the null hypothesis. In this example, we're using the altitude that the person is able to make it to on the mountain to decide how much evidence we have against the null hypothesis. So the altitude that the person is able to make it to before the person has to stop is the test statistic. And just like before in our earlier examples, the lowest the test statistic can be is 0, because 0 is the lowest altitude that the person can climb to. If the person stops at 0, it just means that the person didn't even try to climb the mountain. And just like in our other examples, if the test statistic ends up being 0, meaning if our outcome lands at a test statistic of 0, we have no evidence against the null hypothesis. In this case, if the person stops at 0 and doesn't try to climb the mountain, we have no reason to think that the person trained for the climb, because that outcome perfectly lines up with the null hypothesis of no training. And the further the test statistic is above 0, the more evidence we have against the null hypothesis. In this case, the higher the person is able to make it up the mountain, the more evidence we have against the null hypothesis of no training. And since 3,000 feet is our critical value, 3,000 feet is the point where the test statistic is high enough for us to
be convinced that the null hypothesis is wrong, and that we think that the alternative is true. Now I'll do another example. In the next example, the test statistic can actually go in two different directions. Let's say that this person right here is playing a game in which the person throws a ball straight up into the air, and the person waits to see where the ball lands on the ground. And the person scores more points by having the ball land further from where the person is standing. And we're interested in whether the person is cheating at the game. If the person is standing right here at the center where the person should be standing, then the person isn't cheating. But if the person stands further to the left or further to the right, the person is cheating at the game. So these are our two possibilities. The null hypothesis is a possibility of no cheating. Because the null hypothesis is the possibility that something is absent or missing. And the alternative hypothesis is the opposite. The alternative is a possibility that something exists or something is happening. So the alternative hypothesis would be the possibility that the person is cheating. These are our two competing possibilities, and only one of them can be true. In order to make our decision about whether we should reject the null hypothesis and accuse the person of cheating, we're going to wait to see where the ball lands, and then we're going to count how many feet the ball landed away from where the away from this center point right here where the person should be standing. So we know that this is where the person should be standing, at the center right here. And let's say that this is 5 feet from the center where the person should be standing. This is 10 feet. And this is 15 feet. This is 0. And this is 5 feet in the other direction. And 10 feet and 15 feet. And we know that if the null hypothesis is true, and the person isn't cheating, then in that situation, outcomes further this way, further away from the center, are less and less likely, and outcomes further in this direction are less and less likely, because if the null hypothesis is true, and the person is standing at the center right here, then the ball should land somewhere near the center. The ball is unlikely to make it too far in this direction, or too far in this direction. So we can say that in both of these directions, the outcomes are getting less and less likely in the situation of the null hypothesis being true. So we have a test statistic. Our test statistic is the number of feet between where the ball lands and the center point right here where the person was supposed to be standing. So as we go further in this direction, the outcomes are less likely, and they're less likely when the null is true. And also in this direction, the outcomes are less likely when the null is true and the person isn't cheating. And since the outcomes are getting less likely to happen when the null is true in both directions, the outcomes are also showing more evidence against the null hypothesis, meaning more reason to think that the null hypothesis isn't true and that the person is cheating. And just like in our other examples, if our outcome ends up being 0, then we have no evidence against the null hypothesis. If the person throws the ball straight up in the air and the ball lands right straight back down at 0, we have no reason to think that the person was cheating, because that outcome lines up perfectly with the null hypothesis. Meaning, if the ball lands right at 0, that is perfectly consistent with the idea that the person was standing right here and that the person wasn't cheating. But outcomes further out here and further out here are showing more and more evidence against the null hypothesis, meaning these outcomes out here would give us more and more reason to think that the person was cheating. And at a certain point out here, we're going to have a critical value where if the ball lands this far in this direction, we'll reject the null hypothesis and conclude that the person was cheating. In this case, if it lands too far out in this direction, we'll conclude that the person was standing too far to the left. We'll think that the person was cheating by standing out too far this way. And out here, we'll also have a critical value where if the ball makes it that far out this way, we'll reject the null hypothesis and conclude that the person was cheating. But if the ball makes it to the critical value out here, we'll conclude that the person was cheating by standing too far out in this direction. So if this critical value is reached on the left side, we'll conclude that the person was cheating by standing too far to the left. And if the critical value is reached on the right side, we'll conclude that the person was cheating by standing too far to the right. Now we have to decide where those two critical values will be. Let's say we know that when the null hypothesis is true, and the person is standing right here at the center where the person should be standing, this point out here at 15 only has a 5% chance of being reached. And this outcome out here at 15 also only has a 5% chance of being reached. In that case, these would be our two critical values. They would be the starting point of the rejection regions. Because in this example, we actually have two rejection regions. One rejection region starts at this critical value and goes out to the left. And the other rejection region starts at this critical value and goes out to the right. So we have two critical values and two rejection regions. So in the situation of the null hypothesis being true, meaning in the situation in which the person isn't cheating and is actually standing at the center, the ball only has a 5% chance of making it more than 15 feet from the center, meaning the ball only has a 5% chance of landing in one of the two green areas. So if if the ball does land more than 15 feet from the center, then we'll reject the null hypothesis and conclude that we think that the alternative is true and that the person was cheating, because in the situation in which the null hypothesis is true and the person isn't cheating, an outcome out here is unlikely to happen, and an outcome out here is also unlikely to happen. So that's why outcomes out here and outcomes out here cause us to reject the null hypothesis.
One last thing I wanted to talk about is how it's possible to make a wrong decision during a hypothesis test, meaning the decision that you make in a hypothesis test is it's not a proven conclusion. You're just making a conclusion about what the evidence suggests to be true. So let's go back to situation 2. Let's say I hear 15 noises inside of the walls of my house during the day, and I decide that that there's a rat living inside the walls of my house. I reach that conclusion. I've made a conclusion because of the evidence that I have, meaning the evidence that I gathered with my ears led me to conclude that there must be a rat inside the walls of my house. But that could be a wrong conclusion, meaning it could just be that I did hear 15 random noises during the day. So that would be one possible wrong conclusion. In that situation, I've rejected the null hypothesis, and I decided that there was a mouse living inside the walls of my home. But the null hypothesis is actually true, meaning there really is no mouse inside the walls. Now, I said it would be unlikely for me to hear 15 random noises during the day just by chance, but that still could happen. I mean, even if it's unlikely, it's still possible for me to hear 15 random noises. It's also possible that if I don't hear any noises during the day, and I conclude that there's no mouse living inside the walls of my house, it could still be that there really is a mouse living inside the walls, but it's just a very quiet mouse that's not making any noise. So if I decide to assume that the null hypothesis is true, I could be making a wrong conclusion, because it could be that the alternative really is true, and there really is a mouse inside the walls. So there's two possible wrong conclusions that can be made in a hypothesis test. One wrong conclusion is rejecting the null hypothesis when it shouldn't be rejected. Meaning rejecting the null hypothesis and deciding that the null hypothesis is wrong when the null hypothesis really is true. That mistake is called a type 1 error. So a type 1 error is made when a person rejects the null hypothesis and the null hypothesis really is true. So if I conclude that there is a rat living inside the walls of my house, I've rejected the null hypothesis. But if the null hypothesis really is true and there is no rat living in the walls of my house, then I made a type 1 error. Another wrong conclusion is when you don't reject the null hypothesis and you assume that the null is true, but in reality the alternative is actually true. That's called a type 2 error. So if I don't hear any noises during the day and I assume that the null is true, but it turns out that the alternative is actually true, and it's just a quiet mouse, then I've made a type 2 error. So you can think of it this way. A type 1 error is citing with the alternative hypothesis when the null is actually true. A type 2 error is citing with the null hypothesis when the alternative is actually true. We can make a quick diagram of that. So here we have reality, what's actually true. Reality could be that the null is true, or it could be that the alternative is true. And we also have the decision that's made, meaning the conclusion that the person makes. The decision could be for the null hypothesis, which means the null is not rejected, or it could be a decision for the alternative, meaning meaning when you reject the null hypothesis, this decision right here, when you decide that the null hypothesis is false and the alternative is true, but it turns out that the null is true, that's a type 1 error. So type 1 error is deciding that there is a mouse when there is no mouse. If you decide to assume that the null is true, and you give it the benefit of the doubt, but it turns out that the alternative is true, that's a type 2 error. So deciding that there's no mouse when there really is a mouse would be a type 2 error. The other two are correct decisions. And when we use the word error, it doesn't mean that the person who was collecting the data made a mistake. It doesn't mean that the person did the study improperly or didn't plan out the study very well. It doesn't mean an error was made by the researcher. What it means is that it simply means that a wrong conclusion was made. And the reason why these two wrong conclusions are made sometimes is simply because the evidence that you gather can sometimes mislead you. Like I said, if somehow 15 random noises come from the walls of my house during the day, that's misleading evidence, meaning those 15 noises show strong evidence for me to believe that there is a mouse. So what's happened in that situation is that I've just observed some misleading evidence that led me to a wrong conclusion, but it doesn't mean that I did anything wrong as a researcher. So the analogies that people usually give for type 1 error and type 2 error is that a type 1 error is like sending an innocent person to jail. Meaning, if you think of the null hypothesis as being no guilt, the absence of guilt, and the jury rejects that null hypothesis and concludes that the person is guilty, but it turns out that the null really is true and the person is not guilty and innocent, then that's a type 1 error. A type 2 error is like letting a person who really is guilty go free, because in that situation, the alternative is true, meaning the person is guilty. There is guilt. But the jury has decided to stick with the null hypothesis and conclude that the person is innocent. That's a type 2 error. And those mistakes can sometimes be made in jury trials, just like how they can be made in the types of examples that I've covered. The good news is that if studies, or meaning data collection, is done properly, then these two errors happen much less often, and the correct decisions happen much more often. So over time, more studies will lead to correct decisions, and fewer studies will lead to the type 1 and type 2 errors. But that's only if, like I said, that's only if studies are done properly. I want to talk about the idea of a p-value in a hypothesis test. To explain the idea of the p-value, I'm going to use this same example we were talking about before, in which a person is climbing a mountain, and we want to know if the person trained for the climb. In this example, the null hypothesis was a possibility that the person did not train for the climb, and the alternative hypothesis was a possibility that the person did train for the climb. And we were imagining that out of all people who climb the mountain without training, 60% make it to this area less than 1,000 feet, but they stop there. We were also imagining that out of all untrained climbers, 30% make it into this area between 1,000 and 2,000 feet, but then they stop somewhere in this area. And we were imagining that out of all untrained climbers, 6% make it into this area between 2,000 and 3,000 feet, and then they stop there. We were imagining that 4% of untrained climbers make it to this area right here, but then they stop in this area between 3,000 and 4,000 feet. And we were imagining that out of all untrained climbers, 1% make it to this area here between 4,000 and 5,000 feet. And we set our critical value at 3,000 feet because 3,000 feet was the point that's only reached by 5% of untrained climbers, because we can see that out of all untrained climbers, only 5% make it into this area above, starting at 3,000 feet and going up to the top of the mountain, because 4 plus 1 is 5%, so a total of 5% of untrained climbers make it to 3,000 feet or higher. So this area is our rejection region. We said that if the climber makes it to 3,000 feet or higher and ends up in the rejection region, we'll reject the null hypothesis and conclude that we think the alternative is true, because if only 5% of untrained climbers make it into the rejection region up here, what that means is that if our climber did not train, then our climber only has a 0.05 probability of reaching the rejection region. So, in other words, if the null hypothesis is true and the climber did not train, then the climber only has a 0.05 probability of being one of the 5% of untrained climbers who make it into the rejection region. That's why if the climber does end up in the rejection region, we think the null hypothesis could be true, but if the null hypothesis is true and the climber did not train, then the climber would have had to have been lucky to make it up that high. It wouldn't be likely to happen in that situation. So, if the climber makes it into the rejection region, we conclude that we think that the climber did train and that the alternative is true. Now let's talk about the idea of a p-value. The definition of a p-value is the probability of getting a certain outcome or an even greater outcome when the null hypothesis is true. So I'll write that up here. These altitudes on the side of the mountain are the different values of the test statistic, and each value of the test statistic has its own p-value. So let's try to think about what the p-value of each of these values of the test statistic would be. Let's start with 1,000. The p-value of 1,000 would be the probability of the climber reaching 1,000 or higher when the null hypothesis is true, meaning when the climber did not train. So in other words, the p-value of 1,000 feet is the probability of, the p-value of 1,000 feet is the probability of the climber reaching this red area right here when the null hypothesis is true, because this red area is everything that's 1,000 feet or higher. Now let's think about what the p-value of 2,000 feet would be. The p-value of 2,000 feet would be the probability of the climber reaching 2,000 feet or higher when the null hypothesis is true, meaning when the climber did not train. I'll mark out this area in a different color. The green line covers everything that's 2,000 feet or higher, so the p-value of 2,000 feet would be the probability of the climber reaching this green area when the null hypothesis is true, meaning when the climber did not train. The p-value of 3,000 feet would be the probability of the climber reaching 3,000 feet or higher when the null hypothesis is true. So I'll mark this off in a different color. I'll mark it off in blue. So the p-value of 3,000 feet would be the probability of the climber reaching this blue area without any training when the null hypothesis is true. Now let's think about the p-value of 4,000 feet. The p-value of 4,000 feet would be the probability of the climber reaching 4,000 feet or higher when the null hypothesis is true and the climber did not train. So I'll mark this off in brown. I'll mark off the area of 4,000 feet and above in brown. So the p-value of 4,000 feet would be the probability of the climber reaching this brown area of 4,000 feet or higher when the null hypothesis is true and the climber did not train. So now we understand the idea of the p-value. Now let's try to see if we can figure out what each of the p-values would equal. So how do we find out what the p-value of 1,000 feet would equal? Remember that the p-value of 1,000 feet is the probability of an untrained climber making it to 1,000 feet or higher. In other words, it's a probability of the climber making it to 1,000 feet or higher in the situation of the null hypothesis being true. To find out the probability of an untrained climber making it to 1,000 feet or higher, we have to first find out what percentage of untrained climbers make it to 1,000 feet or higher on this mountain. Once we find out what percentage of untrained climbers make it to 1,000 feet or higher, we can change that percentage to a decimal, and then that decimal will be the probability of our climber making it to 1,000 feet or higher without any training. In other words, that decimal will be our p-value for 1,000 feet. Now let's find out what percentage of untrained climbers make it to 1,000 feet or higher. Well, we know 30% end up in this area, and 6% end up in this area, 4% end up in this area, and 1% end up in this area. So what we need to do is we need to add all of these percentages that are above 1,000, and then that total percentage will be the percentage of all untrained climbers who make it to 1,000 feet or higher. So when we add these numbers, 30 plus 6 is 36, 36 plus 4 is 40, and 40 plus 1 is 41%. So the total of all the percentages that are above 1,000 feet is 41%. So this means that 41% of untrained climbers make it to 1,000 feet or higher. Now we just need to change that percentage to a decimal, and that'll be our p-value for 1,000 feet. So here's 41%. To change that to a decimal, we have to move the decimal point 2 places to the left. In other words, we have to move it 2 digits to the left. Right now, the decimal point is at the end of the number, so we will move it 2 digits to the left, and then the decimal point will end up being right here, in front of the number. And then after we've moved the decimal point 2 digits to the left, we just take off the percentage sign, and we have 0.41. So we just found out that the p-value of 1,000 feet is 0.41. So in the situation of the null hypothesis being true, meaning in the situation in which our climber did not train for the climb, the climber has a 0.41 probability of making it to 1,000 feet or higher and ending up somewhere in this red area. Now let's find the p-value of 2,000 feet. We can find that p-value the same way that we did when we found the p-value of 1,000 feet. In order to find the p-value of 2,000 feet, we have to add these percentages that are above 2,000 feet to find the total percentage of untrained climbers that make it to 2,000 feet or higher. In other words, we need to find the total percentage of untrained climbers that make it to this green area that starts at 2,000 feet. To do that, we can add the 3 percentages that are above 2,000 feet. So 6 plus 4 plus 1 is 11%. So 11% of all untrained climbers make it to 2,000 feet or higher on this mountain. So we need to change 11% to a decimal. To change 11% to a decimal, we take the decimal that's at the end of the number and we move it to the front. We move it 2 digits to the left. We put the decimal right here, and then we take off the percentage sign. And our decimal ends up being 0.11. And then that decimal is the p-value of 2,000 feet. So since 11% of all untrained climbers make it to 2,000 feet or higher on the mountain, the probability of our climber making it to 2,000 feet or higher without any training is 0.11. So that's the p-value of 2,000 feet. So in the situation of the null hypothesis being true, and our climber having not trained for the climb, the climber has a 0.11 probability of making it into this green area that starts at 2,000 feet. Now let's find the p-value of 3,000 feet. To do that, we just add the percentages that are above 3,000 feet to find the total percentage of untrained climbers that make it to 3,000 feet or higher. The 2 percentages that are above 3,000 feet are 4% and 1%. When we add those 2 percentages, we get 5% because 4 plus 1 is 5. So 5% of all untrained climbers make it to 3,000 feet or higher and end up in this blue area. So to find the p-value of 3,000 feet, we have to change 5% to a decimal. And since we only have 1 digit right here, we have to add a 0 in front so that we can move the decimal point 2 places to the left. So right now the decimal point is right here. Now we move it 2 digits to the left, and the percentage becomes, the decimal becomes 0.05, and then we take off the percent sign. So we've just changed 5% to a decimal. When you change 5% to a decimal, it becomes 0.05. So the p-value of 3,000 feet is 0.05, because since 5% of all untrained climbers make it to 3,000 feet or higher, our climber has a 0.05 probability of making it to 3,000 feet or higher without any training. So we can see that you can, when you take a percentage of how often something happens and you change it to a decimal, that decimal is the probability of that thing happening.
So now let's find the p-value of 4,000 feet. We need to, before we can do that, we need to find out what percent of untrained climbers make it to 4,000 feet or higher on this mountain. We can see that only 1% of untrained climbers make it to 4,000 feet or higher and end up in this purple area. So when the null hypothesis is true, this purple area is only reached 1% of the time. So if we want to change this to a p-value, we just take 1% and change it to a decimal. We're not going to add 1% to anything because 1% is the highest percentage, and there's nothing above to add it to. We already know that 1% make it into this purple area. So to change it to a decimal, we need to add a 0 to the front. And then just like we did up here, we move the decimal point 2 places to the left. And then we take off the percentage sign. And then our p-value is 0.01. Because we've changed 1% to a decimal. And once we change the percentage to a decimal, we have our p-value. So in the situation of the null hypothesis being true, meaning in the situation of our climber not training for the climber has a 0.01 probability of making it to 4,000 feet or above. In other words, you could just say that the probability of an untrained climber making it to 4,000 feet or higher and landing in this purple area is 0.01, which isn't a very high probability. So let's think about 3,000 feet, which was our critical value. Before we said that 3,000 feet was a critical value and everything above 3,000 feet, or everything at 3,000 feet or higher, was the rejection region. And we decided that 3,000 feet would be the critical value because only 5% of untrained climbers make it to 3,000 feet or higher, which means that our climber would only have a 0.05 probability of making it to 3,000 feet or higher without any training. So you can see that the critical value has a p-value of 0.05 because the critical value is the point that has a 0.05 or 5% probability of being reached when the null hypothesis is true. So the critical value will have a p-value of 0.05 in a hypothesis test, and all values of the test statistic that are below the critical value will have p-values that are above 0.05, because you can see that these values of the test statistic that have p-values above 0.05 are below the critical value. 1,000 and 2,000 feet are below the critical value. And we can see that outcomes or values of the test statistic that are above the critical value have p-values that are below 0.05 because 4,000 feet is above the critical value and it has a p-value of 0.01. So if we get an outcome that's below the critical value, so if we get an outcome with a p-value above 0.05, it means that our outcome did not reach the critical value and we don't reject the null hypothesis. If we get an outcome with a p-value of exactly 0.05, it means that we barely reach the critical value. It means that our outcome is exactly at the critical value and we do reject the null hypothesis. If we get an outcome with a p-value below 0.05, it means that our outcome is past the critical value and we do reject the null hypothesis because we're in the rejection region. So all outcomes with p-values of 0.05 or less are in the rejection region and lead you to reject the null hypothesis. Because if we reach
If our outcome reaches exactly at the critical value, then we have a p-value of 0.05, and we're barely in the rejection region. And if you have an outcome with a p-value below 0.05, it means you're even further into the rejection region, and you reject the null hypothesis also. So you could say that all outcomes with p-values of 0.05 or lower lead you to reject the null hypothesis. And all outcomes with p-values above 0.05 lead you to not reject the null hypothesis. Meaning, if your p-value is above 0.05, you fail to reject the null hypothesis, meaning you continue to assume that the null is true. I now want to look at an example of calculating p-values with a test statistic that can go in two different directions.
This is the game that we were talking about before, in which a person has to stand at the center spot right here and throw a ball straight up in the air. After the person throws the ball up in the air, the person waits for the ball to drop back down to the ground, and the person earns more points if the ball lands further away from the center spot where the person was standing. And the rule is that the person has to stand at this center spot right here. If the person stands out this way, the person is cheating. And if the person stands out this way, the person is cheating. And we were interested in whether or not this person was cheating. And we were going to check to see where the ball dropped down to make a decision about whether we thought the person was cheating. In this example, the null hypothesis was the possibility that the person was not cheating, and the alternative hypothesis was the possibility that the person was cheating. And we said that in the situation of the null hypothesis being true, meaning the situation in which the person is not cheating and the person is standing at the center spot right here, the ball is likely to fall somewhere near the center and is unlikely to fall too far out this way or too far out this way. Which means that if the ball does fall too far out this way, we suspect that the person was cheating by standing to the left of where a person should have been standing. And if the ball lands too far out this way, we suspect that the person might have been cheating by standing out toward the right of where the person was supposed to be standing. So what would the p-values be in this example? Just like in the last example, every possible value of the test statistic down here has its own p-value. So the p-value of 5 feet would be the probability of the ball landing 5 feet or more from center in a situation in which the null hypothesis is true and the person is not cheating and is standing at the center. The p-value of 10 feet would be the probability of the ball landing 10 feet or more from center in a situation in which the null hypothesis is true and the player is not cheating and is standing at the center. And I'll explain this idea by putting some colors down here. The blue line is going to cover all areas that are 5 feet or further from center. So the p-value of 5 feet would be the probability of the ball landing in one of these two blue areas when the null hypothesis is true and the player is standing at the center. I'll mark all of the areas that are 10 feet or further from center in red. The p-value of 10 feet would be the probability of the ball landing in one of these two red areas when the null hypothesis is true and the person is standing at the center. The p-value of 15 feet would be the probability of the ball landing 15 feet or more from center in the situation of the null hypothesis being true. So the p-value of 15 feet would be the probability of the ball landing in one of these two green areas when the null hypothesis is true and the player is standing at the center. The p-value of 20 feet would be the probability of the ball landing 20 feet or more from center in the situation of the null hypothesis being true and the player not cheating. So the p-value of 20 feet would be the probability of the ball landing 20 feet or more from center when the null hypothesis is true and landing in one of these two orange areas. So how can we find out what the p-value of each of these outcomes are? In order for us to calculate the p-values, we have to know, out of all people who play this game fairly and don't cheat, what percentage of people have outcomes in each of these areas on the number line. Let's say that out of all people who don't cheat and play the game fairly, 40% have outcomes in which the ball lands in this area right here between 0 and 5 feet to the left. And 40% of people who play the game fairly have outcomes in which the ball lands in this area right here between 0 and 5 feet to the right. And let's say that out of all people who play the game fairly and don't cheat, 7.5% have outcomes in which the ball lands in this area right here between 5 feet and 10 feet to the left. And let's say that out of all people who play the game fairly, 7.5% also have outcomes in which the ball lands in this area right here between 5 feet and 10 feet to the right. So as we go further from center, we're seeing that the outcomes out here are happening less often because we can already see that 80% of the time the ball is landing in this area between 5 feet and 5 feet when the game is played fairly, and the ball only lands in this area 7.5% of the time and only lands in this area 7.5% of the time. Let's now imagine that out of all people who play the game fairly, 6% have outcomes in which the ball lands in this area right here between 10 feet and 15 feet to the left of center. And out of all people who play the game fairly, 6% have outcomes that land in this area right here between 10 feet and 15 feet to the right. I'm actually going to have to change these two percentages to 30 and 30, just so that all of my percentages add up to 100%. Now let's say that out of all people who play the game fairly, 2.5%, 4% have outcomes that land in this area right here between 15 and 20 feet to the left. And 4% have outcomes in which the ball lands in this area right here between 15 and 20 feet to the right. And out of all people who play the game fairly, 2.5% have an outcome in which the ball lands all the way over here in this area that's more than 20 feet to the left. And it makes sense that the ball wouldn't land out here very often when the null hypothesis is true, because when the null hypothesis is true and the person is standing at the center, the ball has to travel all the way out here. It has to travel more than 20 feet to make it all the way out here, and the ball isn't likely to travel that far. The ball is more likely to land somewhere closer to the center. And let's also say that out of all people who play the game fairly, 2.5% have outcomes out here that are more than 20 feet from center. So 2.5% of them have outcomes in which the ball lands in this area right here. And it also makes sense that when the null hypothesis is true and the player is not cheating, the ball doesn't go out here very often, because when the null hypothesis is true and the person is standing at the center, the ball has to travel a long distance to make it all the way out here, and that's not likely to happen when the person is throwing the ball straight up in the air. When the person is throwing the ball straight up in the air, the ball is likely to fall somewhere near where the person is standing. For example, we can see that when the person is not cheating and is standing right here, the ball lands somewhere in this black area 60% of the time. So most of the time it lands in this black area right here, and the ball makes it into these areas out here and these areas out here less often. So now let's calculate the p-values. Let's start with 5 feet. To find the p-value of 5 feet, first we have to find out of all the people who play the game fairly and don't cheat, what percentage of them have outcomes in which the ball lands 5 feet or more from center. Well, to find out that total percentage, we have to add all of the percentages that are 5 feet or further from center. All of the percentages that are 5 feet or further from center are these right here. I'm putting them in boxes. We have to add all of these percentages. And if there's 1, 2, 3, 4, there's 8 of them. And if we added all of them, they would add up to 40%. So, out of all people who play the game fairly and don't cheat, 40% of them have outcomes in which the ball lands 5 feet or further from center. In other words, out of all people who play the game fairly, 40% of them have outcomes in which the ball lands in one of these 2 blue areas. And since the ball lands in one of the 2 blue areas 40% of the time when the null hypothesis is true, what that means is that when a player plays the game and is playing the game fairly, and the null hypothesis is true, the ball has a 0.40 probability of landing 5 feet or further from center and ending up in one of the 2 blue areas, which means that the p-value of 5 feet is 0.40. So what we did to get the p-value is we added all of the percentages that were 5 feet or further from center, and they added up to 40%. And we found out that when the null hypothesis is true, the ball lands 5 feet or further from center 40% of the time. And then we change that percentage to a decimal by moving the point 2 places to the left, and it became 0.40. We move the point 2 places to the left and take off the percent sign, and we get a decimal, and that decimal is the p-value. So the p-value of 5 feet is 0.40. I'll put 0.40 under 5 feet, and this is also 5 feet, so that also has a p-value of 0.40. So what this p-value of 0.40 is saying is that in a situation in which the null hypothesis is true and the player is standing at the center, there's a 0.40 probability that the ball will land 5 feet or more from center and end up in one of the two blue areas. Now we can go through the same steps to find the p-value of 10 feet. To find the p-value of 10 feet, we have to add all of the percentages that are 10 feet or further from center, and I'll put a red box around those percentages. We're going to be adding 6 percentages because we have these 3 percentages out here and these 3 out here, because these are also 10 feet or more from center. So let's think about what these 6 percentages add up to. 6 and 4 adds up to 10, and 6 and 4 adds up to 10. So these 4 boxes add up to 20. And then 2.5 plus 2.5 is 5. So all 6 of these percentages in the red boxes add up to 25%. So what that means is that out of all people who play the game fairly, 25% of them have outcomes in which the ball lands 10 feet or more from center. In other words, when the null hypothesis is true, the ball lands 10 feet or more from center 25% of the time. So now what we need to do is take this percentage and change it to a probability. We can do that by taking the point and moving it 2 places to the left, like we did before, and putting the point in front of the number. Then we take off the percentage sign, and now we have our p-value. The p-value of 10 is 0.25. So I'll put 0.25 here, and I'll put 0.25 out here. So what this p-value of 0.25 is saying is that in the situation in which the null hypothesis is true and the player is standing at the center, the ball has a 0.25 probability of landing 10 feet or more from center and ending up in one of the 2 red areas. Now let's find the p-value of 15 feet. To do that, we have to find out of all people who play the game fairly, what percent of them have outcomes in which the ball lands 15 feet or more from center. So now let's look at the percentages that are 15 feet or more from center. I'll put these ones in green. So we're going to be adding these 4 percentages that are 15 feet or more from center. When we add these, we get 13%. These 4 percentages in green add up to 13%. And just like before, to get the p-value, we need to change that percentage to a decimal, because this percentage right here is saying that when the null hypothesis is true and the player is standing at the center, the ball lands 15 feet or more from center 13% of the time. In other words, out of all people who play the game fairly, 13% of them have outcomes in which the ball lands 15 feet or more from center. So if we change this to a decimal, then we have the probability of a player who's not cheating having an outcome in which the ball lands 15 feet or further from center. So the p-value of 15 feet is 0.13. What this p-value of 0.13 is saying is that in the situation in which the null hypothesis is true and the player isn't cheating, the ball has a 0.13 probability of landing 15 feet or more from center. Because remember, the p-value is a probability of getting a certain outcome or an even greater outcome when the null hypothesis is true. So now let's find out what the p-value of 20 would be. Well, to find the p-value of 20, just like before, we have to start by finding out out of all people who play the game fairly, what percent of them have outcomes in which the ball lands 20 feet or further from center. And to do that, to find out that percentage, we have to add this percentage out here, because this is past 20, to this percentage out here that's also past 20. When we add these two percentages together, they add up to 5%, because 2.5 plus 2.5 is 5. So we can see that out of all people who play the game fairly, 5% of them have outcomes in which the ball lands 20 feet or more from center. And we can change that percentage to a probability if we change the percent to a decimal. We have to add a 0 at the front, and then move the point 2 places to the left, and put the point in front of the number, and take off the percent sign, and 5% turns to 0.05, which means that the p-value of 20 is 0.05. So when the null hypothesis is true, and the player is playing the game fairly, outcomes that are 20 feet or more from center happen 5% of the time, and that's why when a certain person plays the game fairly and the null hypothesis is true, that player has a 0.05 probability of having an outcome in which the ball lands 20 feet or more from center in one of these two orange areas. So in the situation of the null hypothesis being true and the player not cheating, there's a 0.05 probability in which the ball will travel 20 feet or more from center and land in one of these two orange areas. That's why the p-value of 20 is 0.05. And remember before we talked about how the p-value, we talked about how the outcome that has the p-value of 0.05 is the critical value. So since 20 is the outcome that has a p-value of 0.05 in this example, 20 feet would be our critical value. So in this example, we have a p-value, we have a critical value of 20 feet out here, 20 feet to the left of the person, and we also have a critical value of 20 feet to the right of the person out here. And this right here is the starting point of the rejection region that goes out to the left right here. And this is the starting point of the rejection region that goes out to the right out here. So we actually have two rejection regions. This orange area is the left rejection region, and this orange area out here is the right rejection region. If the ball lands in this rejection region out here, if we find the ball out here, laying on the ground out here, we'll reject the null hypothesis. We'll reject the idea that the person was playing the game fairly, and we'll conclude that we think that the player was cheating by standing too far out to the left. We're going to think that the reason that the player was able to get an outcome all the way out here is because the player was actually standing further out to the left than the player should have been. If the ball lands in this rejection region out here, meaning if we find the ball laying on the ground out here, what we'll do is we'll reject the null hypothesis, meaning we'll reject the possibility that the person was not cheating, and we'll conclude that we think the person was cheating by standing too far to the right. Because what we'll be thinking is that if the player was standing at the center, and meaning if the null hypothesis was true, the ball would be unlikely to make it all the way out here and land in this orange area. So, since that would be unlikely, what we're concluding is that the player was actually standing too far out this way to the right. And that's why the ball was able to make it this far to the right of the center. We'll be thinking that the reason the ball was able to make it to the orange area is because the player was actually standing out here somewhere and not in the center like the player should have been. And if we find the ball out here and we accuse the player of cheating, we haven't proven that the player was cheating, because it could be that the person really was playing the game fairly and the ball just traveled a really unlikely distance. So it could be, if we find the ball out here, it could be that the null hypothesis actually is true and that the ball just landed a very unlikely distance from center. But since it would be so unlikely for the ball to make it out here when the null is true, we're going to reject the null hypothesis and conclude that we think that the person was cheating at the game. Remember I said that when an outcome lands in the rejection region, there's two possibilities. Either the null hypothesis is true and an unlikely outcome happened, or the alternative hypothesis is true. And that's why when you reject the null hypothesis, you're not making a proven conclusion. You're just making a conclusion about what appears to be true. It's possible to make a graph that shows p-values, and the graph will be a curve that goes over this number line. And I'll show you what that curve looks like. The curve starts at its highest point right here, at the outcome that's most likely to happen when the null is true. And it drops down as the outcomes get less and less likely to happen when the null is true. So this isn't a very good drawing, but the curve looks like something like this, because as the outcomes get less and less likely to happen when the null is true, the curve gets lower and lower. So out here, these outcomes are getting less and less likely to be reached when the null is true, which is why the curve is getting lower and lower. And the outcomes out here are also getting less and less likely to happen when the null is true. So that's why the curve is getting lower in this direction. So as the curve is dropping down, it means that the outcomes are getting less likely to happen when the null is true. meaning when the player is standing at the center and not cheating. And the same thing is happening in this direction. The curve is getting lower as the outcomes are getting less likely to happen when the null is true. And the shape that this curve is following is actually based on the p-values, because if we make a line right here going straight up from 5 feet, and we make another line going straight up from 5 feet right here, then we know that the p-value of 5 feet is 0.40. What that means is that 40% of the area under this curve is 5 feet or further from center. So this area out here and this area out here are make up 40% of the area under the curve, and half of that 40% is in here, and half of that 40% is in here, which means that 20% of the total area under the curve is in here, and 20% of the total area under the curve is in here. So this is 20%, and this is 20%. And 20% plus 20% adds up to 40%. So a total of 40% of the area under this curve is 5 feet or more from center, because this is 5 feet or more from center out here, and this is 5 feet or more from center out here, and all of that area adds up to 40%. And what this p-value of 0.25 means is that 25% of the area under this curve is 10 feet or more from center. So half of that 25% is here in this part of the curve, and the other half of that 25% is out here, starting at 10 and going out this way. And half of 25% is 12.5%. So if we make a line right here, this area in here is 12.5% of the area under the curve, and this area out here is 12.5% of the area under the curve, and they both add up to 25%. If we look at this p-value of 0.13, what that p-value is saying is that 13% of the area under this curve is 15 feet or more from the center, which means that half of that 13% of area is in here, in this area out here, and half of that 15% is in this area out here. So that's this is just showing you how you can think of p-values as being an area under a curve. And this this curve right here that is based on the p-values has a name. It's called the Null Distribution. And the Null Distribution is the distribution of the probabilities of all of the possible outcomes in the situation of the null being true.